the guidelines for the design of lacing. So one by one we will discuss these guidelines. The first one is lacing element must be so placed that the individual part being connected will have slenderness value less than the governing slenderness ratio of the entire built-up member. So if we see over here, so in between the lacing point, the slenderness ratio of individual member or of this individual member in between this lacing point, it should be less than the slenderness ratio of the built-up section Rx and Ry, are the governing value out of these two. So the lacing element should be so placed. So if this R is more, then we can reduce this spacing. When this spacing will be reduced, the R value of this individual member will be reduced, and we can satisfy the condition R should be less than Rx or Ry. Next is, in riveted construction, the effective length denoted by LE of lacing bars for the determination of the permissible stress phi C FCR shall be taken as the length between the inner end rivets of a bar for single lacing. So if we see this bar, this is the lacing element. So the distance between the inner rivets, it is denoted by A, and the effective length LE will be equal to A to calculate the slenderness ratio and phi C FCR value. But if we are using double lacing, mean we have lacing in the cross shape, so in that case LE will be equal to 0.7 A. In welded connection, the effective length shall be taken as the distance between the inner end of the effective weld length connecting the lacing bar to the main member element for a single lacing, and 0.7 for the double lacing. So again, if the weld is up to here like this, so from the end of the weld up to the other end of the weld, we will have this length A, and LE will be equal to A in case of single lacing, and LE will be equal to 0.7 A in case of double lacing. What it means, we consider the length, effective length, from the end of the effective weld up to the other end of the effective weld on the other side. Next guideline is slenderness ratio of the lacing element are limited to 140 for single lacing and 200 for double lacing. Mean LE over R minimum should be less than 140 for single lacing and should be less than 200 for double lacing. Double lacing should be used if the distance between the connecting lines between the lines of welds or fastener in a flange denoted by S is greater than 380. So if this S is greater than 380, then we will use double lacing, otherwise we will use single lacing. And this S is the distance between the fasteners in case of built-up section. So if we use channel section like this, so one rivet will be over here and the other rivet will be over here. So the distance between these rivets will be S. And if we use the channel section face to face, so in that case, one rivet over here and the other rivet over here, so this will be the S value. So if this S is more than 380, then we will use double lacing, and if it is less than 380, we can use single lacing. And in case of single lacing, angle should be more than 60 degree, and in case of double lacing, angle should be more than 45 degree, and this angle is with vertical. We have the section like this, so this theta is with the vertical. And we have already studied effective length will be equal to A or 0.7 A for double lacing, slenderness ratio less than 140 for single lacing and less than 200 for double lacing. And single lacing will be used when S is less than 380 and double lacing when S is more than 380. Next guideline is lacing should be proportioned to provide a shearing strength normal to the axis of member equal to 2% of the total compressive strength of the member. So this is the member, this is its longitudinal axis. So the shearing strength normal to the member VU, it should be equal to 2% of the capacity of this section, the capacity of the section, which is phi C Pn. So we consider VU equal to 2% of phi C Pn, and the lacing element should resist this much shear strength. Next guideline is, this force should be equally divided into lacing elements at a particular cross section. For example, if we see this section, like this. So here we have two faces. So if we use single lacing, so one lacing element will be on one side and the other lacing element will be on the other side. So if we talk about the force in one lacing or in the lacing element on the one side, so that will be equal to Vu over N. So it is written over here, lacing bars may be under tension and compression alternatively. However, the compression in the bar is more critical and the design is performed for it. So it means lacing element will be designed as a compression member. So if N is the number of parallel planes of lacing, shear on one lacing face will be equal to Vu over N. So here we have one plane and here we have the other plane. So it means N will be equal to 2. So Vu or the shear strength will be equal to, in one lacing point or in the lacing element of one face, will be equal to Vu over N or Vu over 2. The next guideline is for single lacing, component of axial compression should provide the required shear component. So if we talk about the force in the lacing element, so we can visualize it like this. So here we have a lacing element and it should resist the shear force equal to Vu divided by N. So if this is Vu divided by N, this angle is theta, so this angle will also be theta. So we can determine the force in this lacing member. So the force in the lacing member, Fu, if we divide this or we find the component of this Fu, it will be equal, in the horizontal direction, it will be Fu sine of theta. And this should be equal to this Vu over N. So from here we can find Fu is equal to Vu over N sine of theta. So this Fu will be the force in the lacing element. So the force in the lacing element can be determined. Here this is the shear force that should be resisted by the lacing element. So if the force in the lacing element is Fu, so if we divide it into horizontal component, the horizontal component will be equal to Fu sine of theta and that component should be equal to Vu over N. So from here we can write this equation. So by simplifying this equation we can get Fu is equal to Vu over N sine of theta. So this is for single lacing, and if we have double lacing at any face, so in that case we need to divide this by 2 because shear force or the force of this lacing will be resisted by the 2 elements, so we need to divide it by 2. So for the double lacing it will become Vu over 2 times N sine of theta, and N is again number of faces. For example, if we use double lacing and we have 2 faces, for example it is a channel section 2 faces, so in that case force in a single lacing element will be equal to Vu over 2 for double lacing and 2 for 2 faces and sine of theta. So our Fu will be equal to this one in this scenario. Okay, next guideline is the transverse center to center distance between the rivets or centroid of the weld may be easily found from the known standard gauge distance of the individual element. For example, if we see this channel section, so we have the standard gauge length given in the ACI manual or AISE code. So when we know this gauge length, the standard gauge length, it means the weld or the rivet should be provided at this location. So if we make a built-up section by using these C section face to face, so in that case one rivet will be over here at a distance G from this web and the other will be on this side from the web. So the spacing between these 2 rivets will be equal to B, mean the total width, the total distance between the web, minus G on one side and G on one side. So it will be B minus 2G. But if these are back to back, so in that case if B is the distance between the webs, so it will be B plus G on one side and G on the other side, plus G plus G. So it will be equal to B plus 2G. So it is written over here. So S is equal to B minus 2G for parts facing each other and B plus 2G for parts facing back to back. Okay, the next is regarding the end plates, the AISC specification states that the end tie plates shall have a thickness at least equal to the 1/50 the distance between the connection line of rivets, bolts or welds, and shall have a length parallel to the axis of the main member at least equal to the distance between the connection lines. Mean the thickness of tie plate should be greater than S/50. S is the distance between the rivets or weld, so S/50, and the length of the tie plate should be equal to S. So if we see, this is the built up section, so at the end we will have tie plates. So the length of tie plate should be equal to S and its thickness should be S/50, and its width should be equal to the width of the built up section. Next is the slenderness ratio L/R of the flanges between the lacing points should not be more than the 3/4 of the overall slenderness ratio of the main member. So if we talk about, we have channel section. If we see in the elevation, so it will look like this. So for example, we have lacing element starting from here and up to here, and the other one in this direction. So for this flange between the lacing points, so the slenderness ratio L/R of the flange between the lacing points, so the slenderness ratio of this flange between the lacing point should be less than 3/4 of the overall slenderness ratio of the main member. So the overall slenderness ratio of the main member, whatsoever is that, the slenderness ratio of the flange should be less than 3/4 of that value. Or if we rearrange this equation, we can get 4.61 L/TF. So slenderness ratio will be equal to this one, and if we rearrange, it will become 4.61 L/TF should be less than R. So R of this section. The next specification is for flat bar for lacing should have the following minimum width considering the minimum edge clearance from center of the rivets. So the section of the lacing element should be such that it should have a clear distance from the center of the rivet or hole up to the edge. It should be 1.5 D. Similarly on this side it should also be 1.5 D. So it means the total width of the section should be equal to 3 D. So this condition should be satisfied. Mean the section, if we draw, so the width of section should be 3 D. So B minimum should be 3 D or more than 3 D. Batten plates is defined as a rigidly connected plate elements used to join the two parallel components of a built-up section. This is designed to transmit shear between the two components of a main member. So we can also use the battens as we have seen in the previous slide. So if we have built-up section like this, so we can use battens like this. So these are rigidly connected. It means we should have at least 2 rivets parallel to the axis of the member, or we should weld these battens with the flanges or with the elements of the individual section. So double lacing shall be joined together at the intersection. So if we are using double lacing, so the lacing elements should be joined at the intersection at this point by using the rivet.